Here we are. We're talking about box culverts and the guide we put together. And so you see a picture of it over on the right. Um, so we used the standard template from the bridge design manual, and then we had to give it a name, a manual number. And so I'll let you guys figure out where that manual number comes from. So let's get going. Um, my purpose today is to go over a couple introductory items and then sort of step in and get through the guidance document itself. So some of it people have seen in the past. We talked about the characteristics of the inventory of culverts, how many of what type of things. We talked about all the past culverts were allowable stress design up until the precast guys, and then they turned into load factor designs. We do have some background on the standard plans that MnDOT's developed since the 1920s coming forward. I'd like to talk a little bit more in depth about just basically getting a cast-in-place concrete culvert modeled in BRR. Spend a bit more time talking about the refinement techniques. And so we've got 4 different techniques which can be deployed to help improve load rating factors. And then the manual itself has a C-box culvert design example and a W-box culvert design example as well. And then we'll finish up with just a couple of miscellaneous topics about, documenting what refinements you use and where you should put them. And we'll talk about things like multi-cell W boxes as well, which need to be handled a little bit differently. So what kind of resources are available to a person doing a load rating on a box culvert for the state aid office? I think the first place to start would be on the file transfer site that Moises set up. On that site are scans of old standard plans for the first culverts with standard plans in Minnesota, the W culverts. There's also C culverts, and also embedded in those PDF files are the early precast concrete box culverts. And Ursula spent quite a bit of time getting things organized and has a spreadsheet that can help people locate what standard plans are available for different types of box culverts. The second major item, is this box culvert guide that you received today, the PDF file. Previously, 2 XML template files were sent out as sort of seed files or starter files to get a W culvert and a C culvert into BRR. And then we have what we call the analysis refinement spreadsheet. And so that has guidance on how to, you input a handful of parameters and outcomes, refinement scale factors, and surcharge heights that can be used to improve your load rating values. And of course, the biggest resource you guys have are Moises and Dave, because they're ready to help you get through your adventures here. So just as a bit of a housekeeping item, in order to make the handling of data simpler in the future, the first choice for any load rating with the box culvert is to complete it inside BRR without any of the special refinements we're talking about. It seems a cleaner way forward, and that's probably a choice you'll be able to make with a precast culvert. You're less likely to be able to do it with a W series culvert. Second choice would be to complete the rating in BRR with the refinements that we'll talk about today. And as Moises talked about, if you get to a spot where everything looks pretty good, the numbers still don't look very good, have a conversation with those guys. It may be appropriate to consider a non-LRFR rating, but you need to talk that through with Dave and Moises beforehand. And Ron brought up a good situation earlier this week. Is there are culverts older than what standard plans are available. So standard plans go back to the 1920s. There are box culverts in the system on the local network that are from the 1900s and 1910s. And for those culverts, you really don't know what's inside of them for reinforcing, and so a PIR may be the only option you have for those very early box culverts. So I usually get scared when people put flowcharts together because it means things are complicated, and I'm hoping that's not the case here with this. And so essentially, this is trying to articulate what I had in those 4 bullet points on the prior slide. If you can get your box culvert modeled in BRR without refinements, and you end up with values over 1.24 for combination vehicles, 1.13 for single vehicles, or over 1.0 and over 1.0 for EVs, complete the rating form, get out of jail, and do not look below. However, if you don't meet those threshold values, you'll need to continue down the flow chart. Some of the refinements we'll talk about are the Giza factor and the approaching wheel, and the releases for the W culverts. Those can be applied holistically in the sense that you can get rating factors that are improved for the top slab, the walls, and the bottom slab with those refinements. And so those are the first 3 to try to improve your values. If you end up applying those 3 refinements and you end up above the magic numbers, you can step out of the flow chart and complete your rating forms. However, if you don't make it after those refinements, there is one more trick in the toolbox for us to use here. Go in and look at your controlling element in the culvert, and if the bottom slab is controlling, we have a refinement to improve the load distribution for the bottom slab to improve that rating factor. Otherwise, it will be the top slab and walls. If they control, you'll need to complete the rating form there. And so when you step out into the rating factor in these lower 2 boxes, you'll need to enter the posting flow chart. And this is a version that's nearly complete, and so it will get updated, and Moises and Dave will be sending out an updated version here in the next few days, is my understanding. So in the prior chart, I had 1.24 and 1.13 for combination and single unit vehicles, and so they come from this chart here. And so you want to make sure you have the version of the flow chart that has the rating factor formula at the bottom. So stepping into the characteristics of the culverts on the local system in Minnesota, there's a lot of them. There's 10,465 as of last April when we got the spreadsheet from Moises. And so Table 1 is inside the guidance document, and it gives you a breakdown of the different types of bridge structures that are classified as culverts. And so cast in place is in the first column, precast, steel, and then others are out here in the right column. And so we're talking about 1,054 concrete cast in place box culverts and nearly 5,000 precast box culverts on the system. If we take a look at what those span dimensions are for the different culverts in the inventory, they vary quite a bit, from something as narrow as 3 feet to as wide as 60 foot for a span. The 60 foot certainly is an outlier, and it's really pretty small numbers until you get, below 20 feet, and the bulk of them is really from 16 feet. Between 8 and 16 feet is where the bulk of the spans will show up on the inventory, and that 8-foot to 16-foot range is something that we've used when we did the refinement work later on. So we were also curious about how many of the box culverts were one cell, how many were 2 cell, and how many were 3 cell or more. And you can see that there are a majority, or the largest fraction is single cell culverts. And again, we've got precast boxes and their distribution here, and we've got concrete box culverts up here. So 1 and 2 spanners definitely dominate what's going on as far as characteristics. If you're out hunting for box culverts and all you know is a year built, you can be pretty assured that if you got something from the 1940s, it's a cast in place culvert. If you got something from the 80s, it's most likely a precast culvert. And so these are the survivors, if you will. As of 2021, there were 368 1930s culverts still in the system. The other thing we wanted to take a look at was how much fill or wearing course depth was over the top of the culverts, because that helps give us an idea of how load distribution takes place. And so when we did, one of our refinements considers how much the wearing course or the overburden helps carry the load and how much of the load bypasses the culvert essentially. We looked at a range between 0 and 6 feet of fill, if you will. And so that covers about 90% of the culverts that are the cast in place culverts we're looking at. Ursula went through the standard specs for construction in Minnesota and sort of, found all the specs going back to the formation of the highway department back in the day. And so after distilling all that information, we basically came up with just a few recommendations. If your culvert was constructed before 1947, you should use an F'(C) for your concrete of 2.5 KSI, which is the default value in the MBE. If your culvert was constructed between 1947 and 2005, you should use 3.9 KSI and 5 KSI if you don't have specific information on the project for the precast culverts. With respect to reinforcing steel, you should use 33 KSI if it was constructed before 1947, 40 KSI between 47 and 72, 60 KSI was used after 1972, and epoxy bars were used after 1988, and 60 KSI should be used for the precast concrete culverts. So the W culverts are the first generation of box culverts that MnDOT put standard plans together for. They're the old dogs, and they started, they have plan sheets from the 1920s, and they were updated into the 1940s. They have a single mat of reinforcement on the inside face of the cell, and so you won't see 2 mats of reinforcement. Typically in these guys, you may see 2 mats of reinforcement for an interior wall. So there's no negative moment capacity over the corners because you've got the construction joints that you don't have continuous reinforcement over. If you're out in the field hunting and you're trying to figure out if you've got any clues as to whether you've got a W culvert or a C culvert, you'll want to look at the fillets in the uppers, and if you've got the construction joint in the middle of the fillet, it's most likely a W culvert, and you won't have, you can dig down a little bit, and if you don't have haunches in the bottom, you can have even more confidence that it's a W culvert. The C culverts were the second generation of cast-in-place culverts, and they have 2 mats of reinforcement in all walls and slabs. Some of them have some crank bars. Both the W's and the C's had what they called normal sections, heavy sections for more fill, and then extra heavy sections at times. So the C culverts are a little more conventional creature to analyze because we do have negative moment reinforcement over the walls and in the corners. There's less manipulation to do with BRR to get a run. Jim Hill was one of the originators of the precast box culverts that were developed back in the 1970s. I think the detail on the left is from 1978, and it shows the haunch being a dimension of 1 foot by 1 foot. You move ahead to the LRFD standards detail shown on the right, and the transition has gone from 1 foot by 1 foot to 12 inches by 12 inches. So not a lot of change in respect to that, and I think just Jim did a nice job sort of making a durable product that hasn't needed to be changed much with time. So now what I'd like to do is just step out of this a little bit, and let's see if I can stop sharing and come back in and just go through just some of the screens people will see inside BRR when they're doing a run here. So let me see if I can share screen again. So hopefully, this is likely the first screen you're going to encounter when you fire up BRR and it's installed on a machine. Hopefully your IT people get it installed, and you'll have to provide your username and password, and you'll have to select which database you're connected to. Let's see. Once you get through that first window, it'll bring up the Bridge Explorer window, and you'll see that up in the left here, and then you can select which bridge ID or which rating project you want to advance or carry forward. And so you can double click on the project you want to work on, and that'll open up additional details on that. There is the opportunity to import things on the top left. Once you double click and enter it, and in this case we're in the cast in place tutorial or the example we have in the manual, you'll see that you have the startup screen, and basically you end up populating the bridge tab and the components tab, and you build a structure down below it. You hit analyze and run is what you essentially do here. So in this particular case, we want to make sure we're doing an LRFR rating based on the LRFD spec, and so you want to make sure you have that selected. If you need to tailor any of the load factors for any of the individual loads, there is the opportunity to adjust those in some of these early screens, and the load combinations as well. You can pick concrete from a standard library, or you can take a standard library concrete and modify it with a new name. And so this is one we've modified. We've taken the Class A concrete and modified it to have the 3.9 KSI that we found based on the old standard specs. And so you can have it compute the modulus of elasticity for you automatically, and most of the other things will populate pretty readily on their own. Similar thing with reinforcing steel. Often we're using the grade 40 reinforcement as appropriate for these culverts, and so it was a standard library item that we could simply select. But if you need to modify it for a particular case, so you have test results showing you've got 55 KSI instead of 40 KSI, you can create a material with those characteristics and use it. The standard soil, we did not really do any manipulation there. We basically took the standard soil 1 that was in the library and used that going forward. And after a while, you sort of get down into the culvert definition part of the example here. And so what you need to do is basically start from a more general definition of the culvert and its environment and work your way down into reinforcing steel and dimensions and put those pieces together. And so one of the first screens will be the culvert definition screen, and this is the location where there's a description box. And so if you end up using refinements later on to improve your rating factors, this is where you would want to note that and say refinement 1, refinement 3 was used, just so people following after you have some breadcrumbs on what's inside the file here. So default materials is pretty straightforward. There's a screen to put in skew angle and barrel length, things of that nature, for traffic loading on top. Also, there is the opportunity to turn on and turn off soil pressure from one side or the other. And this, you would typically think, well, let's apply it everywhere. And that's the right answer most of the time. The multi-cell W culverts will require sort of multiple single cell runs. And part of that may be appropriate to turn the soil off one side when you're doing those. So this is another screen you might want to pay attention to if you've got multi-cell W box culverts on your roster to evaluate. So there are also specs, factors, control factor options to look at here for your boxes. And so I think this is where you can put your condition factor in if you have a deduction for an inspection code rating that's relatively low and you need to change your system factor. Here's the location where you can do that. Control points, I don't think we've done a lot with that, but there is the opportunity to generate user-defined points if you want to get information at special or custom locations. And then you need to tell it how many walls, how thick things are, what's your dimension. So this is a 2-cell 12 by 12 box. Ursula seemed to have the best luck with the horizontal construction joints positioned near the bottom of the haunch here. And so there are multiple horizontal construction joints in your structure. She seemed to have the best luck positioning that value for the top of the box. And so here's the location where you can tell it you do have haunches, and if you do have haunches, what those dimensions are, both in the vertical and the horizontal direction. End conditions. For a typical C culvert or a precast culvert, you'll probably want to leave these values unchecked. If you have a W culvert with only that inner layer of steel, you'll probably want to come back. You'll probably arrive at some pretty low values, and you'll want to come back and consider using the moment releases and side sway support options here in end conditions. Inside BRR, you need to basically build the bar list that was in the standard plans or your project plans, and your tools are relatively straightforward: straight hook bars, corner bars. There are some crank bars, but be careful with your crank bars because you can't flip the crank bar over. So you may have a positive moment region where you want the lower part of the crank bar in the positive moment, and you want the tails up to look like those bars in the W box culvert. You'll need to break those into individual straight segments because you cannot flip the bar over. And so here's number 5 bar with hooks. It's got a 26-foot length. I don't need to bore you with that too much. Here's a vertical 6 bar. And you guys can come back and look at these if you want. They're in the manuals. So here's the material. We're using that 3.9 KSI for this example. The barrel's 134 feet long. BRR does not give you the ability to tweak your impact or dynamic load allowance factors. They're grayed out. And then you need to tell it, what your thicknesses are for the top slab and the bottom slab for each cell, and then the wall thicknesses. So this would be outer wall, mid wall, outer wall. And the box culvert loads. And so this is one you'll probably want to pay a little more attention to as well. And so the start and end fill heights are pretty evident from the figures shown here. But what also is here is the live load surcharge height. And so it used to always be just 2 feet typically, and LRFD's made it a little trickier so that for this particular screenshot, it was 2.18 is what Ursula had calculated. This is the spot where the reduced live load surcharge will get entered. So our last refinement is a way to use an ASTM lateral loading, and we've come up with a way to sort of reduce that and use this input here. So this live load surcharge height is the spot where you can put that in. So that's one to pay attention to. And then you need to step through each of your walls and each of your slabs and put in the top and bottom bars, and those get defined here. And then you need to keep trundling down your navigation window of the bridge components to make sure everything's defined properly. So now we're into an alternative. And then it's time to design and rate. And so you need to, this one's a little fuzzier than I'd like here, but you need to basically pull the vehicles from this left side and drag them over to the right side so they are evaluated. You need to ensure that you've got the LRFR rating method selected, and then you can execute the analysis. Later on, a couple of our refinements will ask you to go into the Advanced tab here, and inside the Advanced tab you can apply a scale factor to some of these loads for the amount of load that gets bypassed, or anyway, so the access to those scale factors is through this Advanced tab here. So you get everything in, you get your alternative defined, and then you can hit the Analyze button. And if things perform appropriately, you'll get some of these icons to darken up over here, and you'll have a window with some blue text that says analysis completed over there. And that will let you know that you've got some results waiting for you in the output side of the program. And with a successful run, you can go in and look at the results, and Ursula likes to look at the single rating level per row. So when the results come through, she usually toggles that on, and then you get axle load and tandem loads, and then your other vehicles would populate below it as well. And so I think we'll skip back here and go back to the PowerPoint. And let's share this. So as I mentioned before, we've got 4 refinements to improve rating factors. Um, we've got the wall releases that produce hinges at the top of the walls and sway fixity. And so this is one that will provide the most benefit for W culverts. We've got an improvement or a reduction in live load for the bottom slab that accounts for extra distribution through the height of the structure, which is refinement 2. The participation of the overburden in carrying load is refinement 3. And then there is an NCHRP report that talks about using an ASTM approaching wheel load instead of the traditional uniform pressure live load surcharge. And so what's going on with the wall hinges and the sway fixity here? And so if you're staying awake late some night and you really can't get to sleep, you can dig out the old BRR culvert analysis modeling solutions and techniques, and that'll put you to sleep pretty quick. But if you're in there, it'll give you the model that they use is a frame model inside BRR to analyze culverts. And so these are just frame elements that go from node to node around the perimeter and up the walls. And as this frame is subjected to external loads laterally and vertically, it produces bending moments, negative moments in the corners, over the walls, and positive moments in the middle of the section. And so if you've got a W section, you need to be able to force it into a positive moment only situation. And so you need to put hinges at the top of those walls. So here's a single cell W section. And so here's that construction joint through the haunch at 45 degrees. And so if you check the moment release at the top and at the bottom, it basically turns this 4-sided structure into 4 simple span beams. And make sure you check the sway prohibited box as well, otherwise it becomes a mechanism, and that's not good for structural analysis programs. And so what you want to do is you just want to turn all your live load from on top and all your dead load from on top into a simple span beam, and you do that by putting a hinge here, and then at the bottom as well. And so as I mentioned earlier, you need to be in the end conditions part of the bridge workspace, and then you can click moment release at top of the walls, at the bottom of the walls, and provide side sway support. And that'll let the model get smart enough for a single cell to analyze the W culverts and come up with a better rating factor. Refinement 2 is taking advantage of the distribution and load, live load, that happens through the structure. So by default, BRR gives you a load intensity at the top of the culvert. And so this is the wheel loads and how they spread out once they get to the top of the culvert. And that intensity is used for the entire frame, if you will. However, if your culvert is controlled by the bottom slab, you can come up with better refined or better rating factors by taking advantage of the fact that this load distribution doesn't know that it can't continue on down as it goes through the height of the structure. So our additional live load distribution refinement basically takes this length at the top of the bottom slab and divides it into the load intensity, which would be applied up here at the top of the top slab, and that ratio produces a scale factor. The one caveat with that, well, I'll get to that later. So basically you populate the refinement spreadsheet. So you put the the data in the green cells here in the spreadsheet, and it pops out the refinement values at the bottom. And so this is the live load distribution to the bottom slab, and you can click on the tab for refinement 2 and you can look behind the curtain and see what's going on. But you can get a fairly substantial reduction in live load for the bottom slab using this refinement. And so the way you would deploy it is you would do your first analysis without the live load distribution to the bottom slab, and you would get rating factors for top slab, walls, and bottom slab. You'd see your bottom slab is controlling, and then you'd come back and go into the advanced tab, and then you would change the scale factor. And then you would run it again, but you can only use the rating factors for the bottom slab from this run. The top slab and wall rating factors aren't valid because the load hasn't distributed for those elements like it has for the bottom slab. So refinement 2, use only if the bottom slab is the controlling element. Note that the rating factors for the top slab and walls from the first analysis, and make sure you compare those original ones to the new controlling rating factors for the bottom slab. And I just want to reiterate, it is not appropriate to use the second run rating factors for the top slab and walls because those have seen the reduced live load that isn't appropriate for them. So our third refinement is participation of the overburden, and this is the one Moises and Dave said took a while, and it did. There's just no other way to phrase it, I guess. And so, but we were pretty thankful that everyone we asked for help came up and gave us feedback, and I think we got to a spot that's safe and appropriate, and it's not as far out there as you might think. But let me tell you the story here a little bit. So we did I jump on it. Ursula did a lot of candy analysis for us. So it's a program that's been around a long time to do soil structure interaction problems. And so basically we did some models where we put some single point load at the middle of the box culvert, and we saw how much thrust was produced at the top corner of the wall, and whatever didn't make it into thrust here was carried by the overburden around the box culvert itself. And so longer spans with thin overburdens, there's not much benefit at all. You get to 6 feet of fill on an 8-foot box, and there's some substantial benefit to this refinement. So in a 3D visualization, this is what we did with our candy model. We had an in situ material, we had a bedding material, we put the culverts of different sizes in that. After that was constructed, we backfilled the material, and then we had 3 layers of overburden we put on top. And so this very top layer was intended to represent either the riding surface on a gravel road, the bituminous surface on a bituminous road, or the concrete pavement on a concrete paved road. And so then we would have the granular or class 5 base course here is the green layer, and then we had some select structural fill below that. And so determining appropriate values took a while because the bridge guys and the pavement guys don't necessarily talk the same geotech talk at times. And so what did all that analysis and conversation lead to? Well, we had those 3 conditions we looked at, sort of a gravel road, a bituminous pavement, and a concrete pavement. And we looked at 8-foot span, 10-foot spans, 7-foot rise culverts, all the way up to 16. And so we were pretty conservative in that this gravel road modulus was assumed to be during spring thaw when it's the softest. The bituminous pavement is in the summer when the bituminous is the softest, and the concrete was assumed to be relatively indifferent to temperatures. And so what does this table tell us? It tells us that if you've got 2 feet of fill on your culvert and you've got a gravel road on top, that overburden will take about 11% of the load, and we apply a fee factor to it, so it's about 5.5% there. Um, Pretty marginal impact if you've got a 16-foot culvert. By the time you soften up the gravel, there's not much benefit to it. One thing you can do is you can sort of work things a little bit backwards, and you can say, well, I've got this gravel road out there. What if I put a 8-inch thick distribution slab on top? What kind of benefit and load distribution might I see? And so um, you can see there's some benefit to putting a distribution slab up on top. So long story short, you'll find these in the refinements for refinement 3 called the DISA deduction. And so those come out in this blue section in the refinement sheet as well. And so these refinement scale factors are independent. They apply for everything because we've computed the amount of load going around the culvert. And so but please note in the description field if you've used that refinement to get to your values. And so, as I mentioned earlier, same place, you get the Advanced tab, and then you change your scale factor here to the appropriate value that spits out from the spreadsheet. Our last refinement is refinement 4, and it's basically utilizing the approaching wheel load as opposed to the standard uniform surcharge that's been used. I talked to Arlen Ottman and I said, Arlen, has it always been the live load surcharge uniform pressure? And Arlen said, yes. And he's retiring now with 63 years of experience, and so that's a pretty good run of uniform live load surcharge here. So the idea came out of NCHRP 1554. There's some pretty smart cookies here that we're sort of trying to figure out what were good modifications to make to culvert load rating to advance the state of the art, if you will. And so they had this graph in their report, and it's a little goofy to look at, but think of this green section as the outline of your culvert with no fill over the top. And this represents your culvert. And so it has incredibly deep fillets, if you will. It goes from a little over 2 feet to nearly 6 feet. So 4-foot fillets are pretty ginormous. But what they're trying to show here is that if you put axle loads on a continuum model, it will generate horizontal pressures on the structure itself. And so I think these original ones were the axle loads came out of Candy models that I'm guessing Dr. Katona ran. And so as he gets closer to the wall, in theory, things get a little less squirrely, but big pressures away at the top, and then they dampen out and quit, or they get lower very quickly. So this vertical orange line represents sort of our standard 120 pounds per square foot lateral live load, the uniform load we all knew. And then this blue line represents an ASTM wall pressure loading that was developed for the evaluation or design of buried pipe structures that came out of the ASTM world. And so basically starts at 800 PSF up at the top and then works its way down. And at about 6 feet of depth, you start to see values underneath what you see with the live load surcharge, the traditional one that we're used to. So the guys in the NCHRP project were pretty bold, I'll give them that. They recommended using the approaching wheel load for culverts with fills less than 2 feet, and you would apply that lateral load the full height. And then they said that if you've got more than 2 feet of fill, say you got 2.5 feet of fill, you don't even need to worry about lateral live load. And I don't think anyone on our team was comfortable ignoring lateral live load. I think we were fairly comfortable using an ASTM standard, but to not consider the live load when you've got 2.5 feet of fill on top seemed a bit beyond where we were comfortable. So if you apply, you plot out what these pressure values look like. Like I said before, they sort of transition at about 6 feet. And so this refinement will usually provide the most benefit if the bottom slab, the top of the bottom slab, is at least 8 feet below the ground line, if you will. So if we took this approaching wheel lateral load graph and sort of spun it 90 degrees, so this is the top of the ground, what we did is we put together a little spreadsheet to let us place our culvert with different heights and different wall heights and figure out where it was loaded. And basically what we're doing is we're grabbing this pressure diagram for the blue section and applying it to the culvert to generate some fixed end reactions that we can use to compare to a uniform load to come up with our scale factor. So way back in the day, back in the 1900s, people did things like moment distribution and slope deflection and matrix analysis methods of structures. And as part of that, you needed to compute fixed end moments. And so what we're doing with our refinement here is we're computing the fixed end moments that come out of the uniform surcharge and computing those end reactions. And then we're taking the pressure diagram from ASTM and computing a point load for every 6 inches of height. And so that's what each of these rows are. We've got a depth of 6 inches for each of these. We're basically computing a point load. Then we generate moments and shears at each end, and we compare those moments and shears after we sum them all up to what's generated over here. And then we take the biggest ratio of those to compute a scale factor. So if we've got a 4 feet of fill over the top of our culvert, and we've got a 1 foot 1 inch tall culvert roof, and it's 4 foot tall box, here's our top of our pressure diagram, here's the bottom. And so if we had a standard 2 foot surcharge, we end up with a reduced surcharge of 1.76 feet. So even with a relatively, shallow box with only a 4 foot rise, we can start to see some benefits pretty quickly. And so you would take that reduced live load surcharge and come back to the box culvert loads tab and insert the reduced value here. So in addition to sort of the general input to the program and the refinements at the end, there are 2 examples, and the examples basically describe what was included in those template files that Moises and Dave sent out earlier. And so there is a C culvert example, the 12 by 12 twin cell box. There's the 10 by 6 W culvert example in there as well. And as I've noted before, that if you use the refinements, please note that in the description field here, so the engineers in the future can follow our work. And then just a note about multi-cell W culverts. And there are a couple of these that I've seen standard plans that do have negative moment reinforcement over the top of the center wall, but others do not. And so if you have the case where you've got a multi-cell W box here where you don't have negative moment reinforcement, you can put your hinges in, which are represented here by the red dots, and that will make the walls fine and you won't have any problem there, but you still have a continuous top slab and you still have a continuous bottom slab, so that when you're applying loads to the roof of the culvert, you're going to generate no moment out here at the corner because you've got a hinge, if you will. You'll generate some positive moment here, and because the top slab is continuous, you'll generate negative moments over the top of the interior wall, and that will cause you to get very low rating numbers. And so what the guys over at SRF did is they just split this into a single cell, if you will, and did not apply earth load to the right here, but did apply earth load to the left and used that as their analysis model. And that makes a lot of sense because it essentially is putting a hinge in here in the top slab where we don't have continuous negative moment reinforcement over the center wall. And so there is a couple pages in the guidance document talking about how to handle multi-cell W culverts without negative reinforcement in the slab. And so if it's a two-cell creature like this where the cells are equal, you really only have one single cell to model. However, if you have narrower side spans and a bigger center span, you'll need to do multiple single cell runs to capture both cases where you've got a longer span here in the middle. So there's a couple pages in the document talking about this particular case. And as Ron brought up before, concrete culverts built before the standard plan, so pre-1920 structures, will require a physical inspection rating. You could get around that if you did do some testing and could confirm where the reinforcement was in the cross section and what kind of reinforcement it was. You could certainly enter it into BRR, but the odds of you having it tested when you go to do your load rating seem remote or slight. And so I guess that's what I had for conversation here.